title is or is not in terms of the grammar, it's pretty clear what we're trying to do here. The issue is, just like with parametrics, we want to be able to find a derivative without having to convert the polar function into rectangular form, all right? Because you end up spending a lot of time just on the conversion, and there's no guarantee you're going to be dealing with a nice enough function that it's going to make the calculus any easier, all right? So the first thing we're going to do is learn what the rule is for finding the derivative of a polar function. Now, I'd like to believe that after I show you this, you're going to come away with the thought of, okay, I'm never going to memorize that formula because I now know where it came from, because the formula is gross, all right? But you'll have an index card for the first test, so you're just going to write the formula down on that and forget everything that I'm saying. But worst case scenario, like, it really is not terrible to invent this formula, all right? So I have this nice diagram here that I stole from some online resource somewhere, but really it's just getting across the idea that, yeah, you could have a polar graph, and with that polar graph, you could have tangents, tangent lines, and you could have normal lines. Normal is just the perpendicular to the tangent, all right? But we're thinking in terms of r and theta, not in terms of x and y. But ultimately, when I come up with a tangent line equation, it needs to be back in terms of x and y. So the first thing I'm going to do is note what x is equal to in terms of r's and thetas. X is equal to r times the cosine of theta. Y is equal to r times the sine of theta. And that just comes from unit circle. Sine of theta is equal to y over r, solve for the y. All right. Now, what I can do is I could take the derivative of x with respect to either r or theta. It does not matter. All right, so I'm going to do it with respect to r. But we have to take the derivative implicitly. All right, because the derivative is being taken with respect to r, I need to make sure that every time I take the derivative of the dr term, I'm going to slap on a dr d theta. I'm sorry, a non-r term, I'm going to slap on a d theta dr. All right, so we're looking at the product of two functions, r and the cosine of theta. So here's my first function, and let me make this purple so I can say that here's my second function. Product rule. First times the derivative of the second, so r times derivative of cosine is negative sine, so negative sine theta, but because this variable is not r, I also have to multiply by d theta dr. Plus the second function, which is cosine, times the derivative of the first function. Well, derivative of r with respect to r is equal to 1. So I'm just going to chuck in a times 1 just so you know, but it's irrelevant. You don't really need it. All right. So then we could do the same thing, but this time with r and sine of theta. So dy dr, first function, r, multiplied by the derivative of the second, cosine theta, but because we're taking the derivative of a variable that does not involve r, I need to differentiate the theta with respect to r, plus the second function, sine theta, times the derivative of the first function, which again is just a 1, because dr equals 1. All right, so at some point, this needs to become dy dx. So I have a dy dr. I don't want the dy dr. I just want a dy. All right. I have a dx dr. I don't want dx dr. I just want dx. So what I'm going to do is take each of these and multiply them all the way through, multiply them by dr. And I'm going to get rid of the calculator for now. So multiply by dr across the board. I think transitioning between apps is what's messing up my pen. All right. But I'm going to write the second one first because ultimately it needs to be dy over dx. So I'm going to put this one right here. And that's going to give me dy is equal. Come on. Let me try doing that. dy equals r cosine theta times dr. I'm sorry, d theta plus sine of theta times dr. All right, so just multiplying every single term by dr. Cancels here, introduces here. It's going to be the same idea for the dx. So dx is going to be equal to negative r sine theta d theta plus cosine theta times dr. All right. Now what I need is dy over dx. Oh, it's funny how that works. All right. Whoop. And whoop. And now you have a rule. So dy dx is equal to r cosine theta d theta plus sine theta dr over negative r sine theta d theta plus cosine theta dr. Rolls right off the tongue. So, you know, like just, yeah, commit that to memory and you'll never have a problem. Obviously not. All right. So it ends up on an index card that you reference. And then after that, it's like, okay, cool. Yeah. I don't remember that formula, so let's Google it. You know, that's really what it comes down to. But this is the origin story behind it, and you can see it's rooted in differential calculus. It's not anything too complicated. And in fact, I would not be shocked if maybe part of this was a question when you were taking Calc 1. I do that. Some other teachers do that. They take something like x equals just this part, x equals r cosine theta, and says, and the question is, using implicit differentiation, because at that point you're just learning about it, find dx dr. And so you come up with this final answer completely out of context. You never really learned what it was for until you're sitting here, you know. And at this point, you still don't know what it's for, so that's great. All right, but anytime you're talking about a derivative, dy dx, it's the slope of the tangent line. Right? It's always that. It's the slope of the line tangent to the curve at any point along the curve. It's defined in terms of all of this other stuff, which is kind of annoying, but still manageable. All right. So when I go to find the derivative, really I'm just thinking about it as like, okay, I need all of these ingredients somehow from this function. Well, I got some thetas. I got a theta there. I got an r. These d thetas and drs, that's a little bit of a different story, but still pretty manageable. You can work your way through that. So let me get you at least set up on number one. So I have r equals 1 plus the sine of theta. All right. So dr d theta is going to be equal to cosine theta. All right, so now I have a relation or relationship between dr, d theta, and cosine theta. All right, so I could figure out dr d theta when theta is equal to pi over 3. That would be cosine of pi over 3, which, based on knowledge of the unit circle, is going to be 1/2. All right, so I have that part of it. Now, what we want to kind of do is develop a way to get this information into the formula. All right, so I used some algebra to clean up my dy dx, and it made it a little bit more concise than it was, and that's fine. But I don't see any dr d thetas in there. All right, I see a d theta and I see a dr, but I never see them at the same time in the form of the ratio. So a simple way of handling that would be to divide each part of the fraction by d theta. All right, so top and bottom of the fraction, I'll do it this way, divided by d theta. So instead of trying to manipulate my dr d theta to make it fit the formula, why not manipulate the formula so that it fits the information that you have? Because the reality is, you're more often going to be given a situation when you have r equals 1 something, anyway, not necessarily 1 plus sine theta, but r equals something, and when you take the derivative, you're going to come up with a dr d theta. So why not take your rule and adjust it so that it fits that information? All right, in which case, you'll end up with r cosine theta plus sine theta times dr d theta over, same stuff really, just different organization, negative r sine theta plus cosine theta times dr d theta. All right, so when I look at this textbook rule, the r cosine theta d theta sine theta dr, like that's one that people have there, like, oh, it's in the book, it's online, whatever, I'll put that on my index card. But this small adjustment to it makes life so much easier, so why not make that adjustment to the rule and make that the new rule, right? You gotta think that way sometimes, all right? So, now I have a way to get my dr d theta in. I need to get an r cosine theta in there. I need to get a sine of theta, all when theta is equal to pi over 3. All right, so let's do that. A piece at a time. So let's figure out what r is going to be at pi over 3. It's going to be 1 plus sine of pi over 3. So that's 1 plus root 3 over 2. Not the nicest thing in the world, but we'll live with it. All right. Then I also need cosine of theta and sine of theta, but that's all unit circle stuff. Yeah, I mean, it never hurts to just write it down, so why not, right? So cosine pi over 3 is equal to 1/2 sine of pi over 3. We already figured that out. That's root 3 over 2. So these are all the ingredients. So I got my dr d theta, I got my r, I got the sine, I got the cosine. So I'm ready to rock and roll on my derivative. Now it's just clean substitution. dy dx specifically, this is the important thing, because dy dx should be in variable form, but because they're saying when theta is equal to pi over 3, I have license to just plug in the numerical values off the bat. So the r value is 1 plus root 3 over 2. The cosine of pi over 3 is 1/2, plus the sine. The sine value is root 3 over 2. The derivative, we figured that out, is 1/2 over the denominator. So we're talking negative r, so negative parentheses 1 plus root 3 over 2, times the sine value, root 3 over 2, plus the cosine value, 1/2, times the derivative value, also 1/2. That's something. Well, that's some good looking calculations right there. Nah, it's disgusting. So a little distributive property, oh, a little gap here. 1/2 plus root 3 over 4 plus another root 3 over 4 over negative root 3 over 2 minus 3 over 4 plus 1/4. I don't feel like getting common denominator, so I'm just going to multiply everything by 4. So 2 plus root 3 plus root 3 over negative 2 root 3 minus 3 plus 1. Two plus 2 root 3 over negative 2 root 3 minus 2. Well, it's all divisible by 2, so might as well. 1 plus root 3 over negative root 3 minus 1. And then if I felt like rationalizing the denominator, I could torture myself even more, I guess. I don't want to do that, so I'm not gonna. Let me actually make that look more like a negative symbol. All right, now that's the slope of the tangent line. They said write the equation of the tangent line. Well, that kind of stinks, because the equation of a tangent line, again, in rectangular form, y equals m times x minus x sub 1 plus y sub 1. What that means is that I need the x and y values for this function also at pi over 3. All right, so it's not over yet. Submitted it as a typo. So x is equal to r cosine theta, and y is equal to r sine theta. So we know what the r value is and the cosine value, so we just have to multiply them. So we don't have to reinvent the wheel, we just got to do the work. And then clean it up a smidge, I guess. Not too much. 1/2 plus radical 3 over 4. And then radical 3 over 2 plus 3/4. All right. So, at long last, I could finally state, so this is the coordinate. I could finally state what the equation of the tangent line is. I was going to say final, but it almost sounded like I cursed. The flubbin' tangent line equation. I actually wasn't, shockingly, the one time. So 1 plus the square root of 3 over the square root of 3 minus 1 times x minus my x coordinate. So 1/2 plus root 3 over 4, close them up, plus the y value of my y coordinate, root 3 over 2, plus 3/4. Holy moly. Look at all that. I'll show you the reason why I find this funny in a sec, but I'm surprised I didn't notice this. That simplifies to -1. So put your function in, get the right domain, and then second trace option 2. All right. It'll create a field once you start typing. At first, it doesn't seem like there's anywhere to type the information, but it creates a field. Yeah, it wasn't until I typed in the pi over 3, hit enter, and it said -1. My first thought was like, what? Screwed that one up. And then I realized these are exact opposites. If I factor out a -1, they cancel. So it actually cleans up nicely. But, well, that's one of the reasons why we have calculators, so that's good news. I could see that I'm going to have a couple horizontal tangents. I got one right here, roughly here. You know, it seems like it's probably right on the 90-degree axis, or the pi over 2 axis. Then I got one over here. And then one over here, two separate horizontal tangents, although it looks like they're probably going to be the same horizontal line. It's just they're going to intersect the graph at two different locations. All right? So these are all horizontal tangents. Then I have two vertical tangents, so I'd have one, I'm just ballparking it like right around here and right around here. So these are vertical tangents. And then any part of a graph that comes to a point is known as either a corner or a cusp. If it bows into the point, it's a cusp, right? Generally, the corners you're not going to have to worry about because those happen with absolute value functions and piecewise functions and things like that. But if you're dealing with a corner, generally it's two separate functions coming together to make a point, all right? And when you think about the absolute value, you say, well, wait a minute, that's just one function. Yeah, but an absolute value function is just shorthand way of writing a piecewise function because it's two separate lines that are coming together to make a point, right? So if it's all part of the same function, odds are it's going to be a cusp. Is it terrible in this case if you didn't know that? No, because you figure, okay, the cusp involves a point. There's only one point. It's not like you have to pick and choose, all right? So you have all these different things that we're looking for. you know, guess and check. I mean, if you're in a pinch, I mean, if it was a multiple choice question on a test or something, I guess you could probably wiggle your way through it. I mean, I already know without doing any work. I mean, just look at the picture. It's at the cusp is at the pole. So I don't have to do any calculus to figure that out. All right. But the horizontal tangents, or at least these two guys, yeah, and the two vertical tangents, because I can take it on faith. You know, I'm pretty confident that this horizontal tangent is at 2, and it's on the 90-degree axis. So, you know, whether I'm going rectangular or polar, I'm pretty confident that I can come up with that one even without doing any calculus. It's the other ones that I need to do the calculus for. All right. So we're going to go through the process of finding the derivative, dy dx. All right. So we got our nice formula up here, r cosine theta plus sine theta dr d theta. All right. The main ingredient, or at least the critically important ingredient, would be the dr d theta. So we have to get that. Now, we already had it. So dr d theta was equal to cosine theta. The issue is, where the last one you could do, because remember you know, it was a couple days ago, but I'll refresh your memories. We went through the whole process by hand, painstaking detail and all that stuff. And I said, oh, and by the way, you can do it on your calculator. I mean, I talked a lot more about it, but that was the gist of it. And then I said, this one, the one that follows, you're going to have to do it by hand. All right. So I'm going to get my formula down here. And then I'm going to do substitution. dy dx is equal to r cosine theta plus sine theta, cripes already, cosine theta. All right, because I'm plugging in the dr d theta on the front. All right, it's dr d theta, which I just discovered is cosine theta. And then on the bottom, negative r sine theta plus cosine squared theta, because we'll just, again, multiply it on the fly. I'll actually write it as cosine times cosine first, but then I'll actually multiply it. Just so I can color code it. All right, so these two components here, this one and that one, those are dr d thetas. All right, let me just clean this up a little bit, because that looks like it might have been like the tail of the r. It's a negative symbol, make it a little bit more obvious. All right, so like I said, algebraically we can clean it up, but we want to think in terms of, you know, if we flash back to Calc 1, and honestly, I'm going to disregard that thought, because I don't know how your instruction was. I'll just tell you what I would have explained to you if you were one of my Calc 1 students. If you're looking for where there's a horizontal tangent, you're looking for where the derivative is equal to 0. All right? So the horizontal tangent, how did I color code that? Red, I think. dy dx is equal to 0. All right, so I'll just kind of hand wave my way through this a little bit. What you would do is set your derivative equal to 0 and then solve. All right, what would happen? The denominator would cancel out. So ultimately, you would just be taking your numerator and setting that equal to 0. All right, so I'd be looking at r cosine theta plus sine theta cosine theta equal to 0. And then for the vertical tangent, So I guess I'll just kind of chuck it off on the side here. I'll bring it in a little. I don't want to cover. You know what, I'll just leave that up there for a second and then talk about it, and then I'll write it. So I'm not moving everything all over the place. For a vertical tangent, you'd want to know where the derivative is undefined. All right, because undefined slope indicates vertical line. All right, so I would take my derivative and set it equal to 1 over 0. And when I do that and cross multiply, the numerator cancels out, and it's just the bottom that's equal to 0. All right, so you know, regardless of whether it's polar or rectangular coordinates, I tell my Calc 1 students this. I'm like, okay, so really couldn't you just, when you're looking for the horizontal tangent, just take the top of the fraction, set that equal to 0? And when you're looking for the vertical tangent, just take the bottom of the fraction and set that equal to 0? Like, wouldn't that just kind of cut out the middleman a little bit? And the answer is absolutely. All right, so I would, like I said, for a vertical tangent, the derivative needs to be equal to some undefined value, which would simplify down to 1 over 0, so you might as well go with that, which ultimately ends up being the negative r sine plus cosine squared equals 0. All right, so this is the pathway towards getting pretty much everything we need. The only thing that we're not addressing here is the cusp. All right, but like I said, you already know where the cusp is. You looked at the picture. It's at the pole. All right. Now, I will talk in a little bit how you would come up with the cusp analytically, because, you know, naturally, if it's going through your mind right now, I'd be wondering the same thing. Well, what if it's not at the pole? Good question, and we'll address that. All right, so we have two equations we could work with here. They're not in terms of one variable, so how am I going to solve for anything? Well, I do know what r is equal to. It's equal to 1 plus sine of theta. So let's just focus on the red equation for now. I'm going to replace the r with a 1 plus sine of theta. Multiply it by cosine of theta, and then add to it the sine theta, cosine theta. Set equal to 0. Little distributive property. It's part of the fun. So we'd be looking at cosine theta plus sine theta, cosine theta, plus another sine theta, cosine theta. Now, as it turns out, I don't want to say that this is an unnecessary step, but sometimes you got to do a step to realize that the step isn't necessarily the best way to go about doing it, because it's at this point where you realize, hopefully, that we have like terms, you can combine them. So we would have cosine plus 2 sine theta, cosine theta. And then at that point, hopefully it becomes a little bit clearer that we have a common cosine that can be factored out. And that's what I was alluding to in that, well, maybe you recognize that up here. I have a common cosine that can be pulled out, and then you could kind of jump right to the simplified form a little bit quicker, all right? But you either see that immediately or you don't. If you don't, then you go down the road a little bit and eventually you see it. And everything's good in the end.
Why don't, could we use the identity theory, like 2 sine theta, cosine theta is equal to cosine 2 theta?
Sine 2 theta. You could, but I think you paint yourself in a corner if you do that. Because then your arguments or the trig functions are not the same. Because one's in terms of theta and the other's in terms of 2 theta.
So we should never use the 2 theta?
Honestly,
How would we know? Like, what's the guidance? Unless you trial and error, right?
that's pretty much it. Like, because that thought did cross my mind.
Right.
And, you know, you kind of play it out and you say, well, what if I do make that adjustment? Where would I go from there? And you look at it and say, well, back where I came from, apparently, because it's not going to do anything for me. But sometimes you don't know until you give it a shot. All right? So a lot of this stuff ends up being related to experience, which is annoying. But, you know, experience is gained through practice. So, you know, you see this problem one time, and now you're on alert for that. All right? Now, it's in factored form. Once it is in factored form, just like a quadratic, you set each of your factors equal to 0 and solve. So I'm looking at cosine theta equals 0, and then 1 plus 2 sine theta equals 0. All right. Now, I can solve my second equation for sine. Subtract the 1 divided by 2. I'll get sine theta is equal to negative 1/2. I have 2 trig functions and the ratios associated with them. The only thing I want to make sure about is that my domain is good for the trig, for the polar function. So 0 to 2 pi seems, because we ended up with this situation last time, it seems like it's giving us the closed loop. All right? Instead of figuring out, because we're doing enough algebra as it is, instead of doing that, just use the technique where we just dial back our theta max a little bit. Instead of going to 6.28, go to 6.2. That's not a 2. 6.2, graph it, and see if it falls just short of being completed. All right, and if it does, then you could be reasonably assured that 2 pi is what closed the loop. All right? Because honestly, I'm not in the business of making trick questions. You know what? Honestly, if I tried to make a trick question, I'd just end up tricking myself. So I don't even bother. So if it looks like, you know, if you get to something like this, it looks like it's almost complete with a 6.2, then it's going to be complete with a 2 pi. It's not like it's going to be like, haha, I got you. It's 2 pi plus 0.01. That's the closed loop. I don't even know how I would figure that out. All right. So what that tells me is that my trig ratios here are in the ordinary 0 to pi unit circle. So all I have to do is think on the unit circle, where is cosine equal to 0? Theta has to be equal to what and what? Pi over 2 and 3 pi over 2. And for the other one? Exactamundo. So on your unit circle for the sine functions, you're just looking for where the y value is equal to negative 1/2. And so that's where you come up with those. For cosine, cosine's always 0 on the y-axis. Because remember, the coordinates are x comma y, cosine comma sine. So if cosine is going to be 0, that means the x value has to be 0. X value 0 on the y-axis, so you just think what angles would be 0 on the y-axis.
I'm sorry, you got those questions from putting finding where cosine was equal to 1/2?
Cosine was equal to 0, and sine was equal to negative 1/2.
Okay.
All in the unit circle.
Oh, I got it, I'm sorry.
Nah, that's cool. All right. So out of all of this mess, we should have the theta values that give us the horizontal tangent. I know they can't all be right, though. The reason I know they can't all be right is because if I go back to my little sketch over here, I identified 3 distinct locations in which there is a horizontal tangent, and this graph doesn't loop back upon itself in any capacity, right? It starts, it goes around, and it comes back. It's not like a limacon where it loops around in, or anything like that. And we know that it's definitely not going around more than once. So one of these is going to be the loser. All right, so we just got to think, well, which one is it? All right. The good news is, all we have to do is go back to the original function, and you can tackle this one of two ways. One way would be to do it by hand, which isn't too terrible, but the other way would be to let the calculator do the heavy lifting using the value function. One of these values is not going to be the horizontal tangent. Instead, because it would never be the vertical tangent, instead one of these values has to be the cusp. So if you go back to the original function, just figure out which one of these angles is going to make an R value equal to 0. The only way that that would happen is if the sine of theta were a -1, because I already have a +1, add to it a -1, now it'll go to 0. So does sine of pi over 2 equal -1? No. Does sine of 3 pi over 2 equal -1? That. All right? So it wouldn't be any of these, right? Because we already know what these angles will give us for sine. It'll give us -1/2. So it's got to be one of these two. Sine of pi is going to give, pi over 2 is going to give us a 1, right? 1 plus 1 is 2. That's giving you that horizontal tangent. All right? The 3 pi over 2 must be giving you the cusp.
But we use only the horizontal, we did the check only for the horizontal tangent, or for the vertical tangent.
We're using the horizontal tangent calculations to check only for horizontal tangent, and whatever's left over could be the cusp. That's the thing. Now, if we did all this work and we only came up with 3 distinct values,
Then there's no vertical.
then we're not worried about the cusp for this one. Then we would go to our vertical tangent calculation and look to see if that presented us with the cusp. So that's what I was saying before. Algebraically, I could show you how you're going to get the cusp, but it's not really a separate calculation. It's embedded in here somewhere. And in fact, it ends up kind of, well, spoiler. If there is a value that's true for both the horizontal tangent and the vertical tangent, that typically is the location of the cusp. All right, so.
It's a follow-up. So if there was a cusp, you would definitely get a horizontal and a vertical tangent in the solution. If you did the horizontal tangent.
If you did just a horizontal tangent calculation, you could get horizontal tangent and cusp, but you would not get the vertical tangent. We still have to do the separate calculation to determine vertical tangent.
I thought by virtue of it not being horizontal, that point would be since it's a cusp, it would be the vertical tangent.
No, because then it's just a cusp. Yeah, that's. So we know that this is the theta value that leads to this point here is 3 pi over 2. All right.
No, isn't it pi over 2?
No,
Pi over 2.
Sine of 3 pi over 2 is.
Oh, you're right.
Every now and then, a broken watch will be right twice a day.
There's a simple way to memorize that.
I just
Left hand rule.
calculator.
30, 40,
Oh, yeah.
60, and then you just, everything is under 2. If you wanted pi over 6, which is 30 degrees, 1 over 2.
Oh, yeah. You just put down the.
Just close the finger that you need to.
Yeah.
And it gives you the answer.
Yeah, I've always meant to teach that, and then I always forget how it works, so I never end up teaching. And so I say, here's a unit circle, memorize it. I'm like, I know there's a hand trick out there, but I can never remember how it works.
What's that though? Hand trick?
Yeah, that's what he was just demonstrating. I still a little.
Pick the left hand, right?
Yeah.
And you number them as 0, 30, 45, 60, 90. If you wanted to get sine of 30, closes, everything is divided by 2. So 1 over 2. 1 over 2. This is the open finger. You forget the top. If you want 45, 2 over.
Just like,
Yeah.
Oh, root 2 over 2. Then root 3 over 2.
And then you do 60. 1 over 2. You're going from the top. Root 3 over 2. 3
Right.
over 2.
Right.
I just knew it as like pi was 180 and then 3 times pi
Yeah,
divided by
both
2.
cosine and
Right,
sine
yeah.
from right
But
side.
he's talking about the
The
radical
numerator always
values.
root two.
So-
Always on the square.
Like you
The
said,
bottom
Right.
is
30, 45, 60.
0, 30, 45, 60, 90.
Okay.
If you're counting for sine with your left hand, you go this way. So whichever, if you wanted to do, say 30, right? Everything below the closed finger is in the numerator.
Yeah.
And that's square root. Everything, every one of them is below, is divided by 2. So it's straightforward.
Right. Yeah, so, I mean, if you have like a fully functioning
Yeah.
hand, which mine is a little iffy, you can think of this your x-axis
Zero.
and y-axis. So 0 and 90.
Right.
Then these are the three important angles in the first quadrant, 30, 45, 60, as you
Yes.
said. And so you're saying that if you want 30, so you pull down the 30 and then just look at the finger, number
Below.
of fingers below.
Yes.
That's, and divide, always remember divided by
Divide by
2.
two.
And then this will give you, the square root of this number gives you the numerator.
That's square root of 1.
Square root of 1, which is 1. Then square root of 2, which is just square root of 2
That's
over 2.
45.
That's 45. And then for the 60, square root of 3
3
over
over
2. Yeah.
And if you do cosine, you
I
come
think
from
I
the-
might actually remember this now.
you come from the right side, you're doing cosine.
Wait,
Value for cosine.
same hand but going
Same
the other
hand,
way?
but
Okay.
you come from right
So
to
still
left.
left hand. So then,
That
oh
is-
yeah, yeah, look at that. Oh, that's cool. So
So
then,
everything on the top is open.
right.
You count from the
So
top.
still root 3 over 2.
No,
root
on the
2 over
top,
2.
from the top side is you counting 1 over 2.
Oh, okay.
1 over 2 is cosine 60.
Right. Yeah, because I accidentally just said that cosine of 60 was root 3 over 2. Good call. Yeah. So root 1 over 2, root 2 over 2, root 3 over 2. Yeah. Ah. Might actually remember that now. Hands are like sore.
And if you do for tan, you just turn it over and take the bottom by the top. And it's the same.
Once the sines and cosines are down, then it's usually just
Yeah.
divide and stuff like that.
Well,
So
you gotta make sure that your fingers are not missing.
yeah, because that's the thing. It's like I could barely contort it the way I just did. It's like tangent is now like okay, now make like a bird, shadow puppets and things like that. You know. Yeah. Everybody walking by while we're taking a test. What the hell are we doing in there? Yeah. So. All right. So. We have these values, and we know that our horizontal tangents. So let me just find the points. So we'll still have to account for that part. That's something else we can deal with in a sec. The horizontal tangents are going to occur when theta is equal to pi over 2, 7 pi over 6, and 11 pi over 6. All right, our cusp is going to occur when theta is equal to 3 pi over 2. All right, now remember, you're not on an island here. Your calculator is there to support you. All right, so you're still, like in the graph, you could select the value function. All right, so second trace, hey, again, this one works a little bit differently, but second trace, and then select value, and then type in your theta. Let's say you were a little iffy and you weren't sure. Type in the 3 pi over 2. And see where it plots. All right, you look at the coordinates, it's plotting it in rectangular form at 0, 0, which is the pole. All right, so you have just confirmed that the pole is the location of the cusp. So even if you didn't pick up on it using the algebraic approach, you'd pick up on it in some capacity.
What's the best way to zoom into this thing? I forgot.
For that one,
You just zoom in and then enter.
yeah, I zoom trig usually, and then make an adjustment from there.
Personally, I like the box.
The box, yeah,
Just sort of outline the whole thing and just.
and then it just kind of gets in.
Can't see
So
that.
try zoom box, and
Can't see
then
very well, do zoom fit, think closer.
yeah, it just like blows it up in your face. Yeah.
Could we use a cheat sheet just to get from the function to know what type of sketch it is?
Oh,
You know,
for the
I have
test?
Yeah.
Well, you have an index card.
Oh, and then-
Yeah, so you just got it down on there, yeah.
Is there a limit to the size of the index card?
There has to be. You have people coming in with like
Life-size
wall-sized
ones?
posters, yeah.
Poster board.
Yeah, exactly. Yeah, 3 inches by 5 inches.
Oh, shit.
Handwritten.
Index card's not a sheet of paper?
What's that?
Not a sheet of paper?
Not a sheet of paper. Second test, you could use a sheet of paper. And then third test is open notes. So you see, we're graduating in the amount of gifts that I'm willing to give you throughout the course. So, we start off where you actually have to remember a few things. So,
You can circle on the board for the test.
there will not be a circle provided for you. Yeah. So, what'd you say, sir?
So Zoom Fit.
Zoom Fit, usually, sometimes it'll let you down, but it's a good place to get started. And then maybe you have to make an adjustment here or there, but a Zoom Fit will create a Zoom that the calculator thinks is the best fit for the graph.
So sometimes it might get it off.
Right, because the calculator doesn't necessarily know what you want out of that graph. So it can be a little iffy, but generally it's pretty good. All right, so then the vertical tangent. Turn my pen on. So again, I'm going to pop in for R, the 1 plus sine theta. So I still have that negative in front. I'll just reproduce that there. 1 plus sine of theta. And then we have the sine theta that's already there, plus cosine squared theta. All equal to 0. All right, so a little distributive property. So we're looking at negative sine theta minus sine squared theta plus cosine squared theta equals 0. Now this one's in a quadratic form, so you're at a point now where it's like, I don't see a GCF, so it's not like the last one where it's going to be quite as simple, but you could apply a trigonometric identity and replace cosine squared theta with, what do we think? All the way back to pre-calc on this baby. 1 minus sine squared theta. All right, and so when we clean this up, we'll be looking at, and I'll just kind of rearrange some things. I have the positive one, which can't be combined with anything. I have the negative sine of theta, also same deal, can't be combined with anything. And then I have a negative 2 sine squared theta. So I was able to combine a couple like terms. All right, so now we have a quadratic, or at least a trig equation in quadratic form. So how do you solve a quadratic? 3 methods. Factoring, which is the preferred method by students everywhere, because that's the easiest one. Completing the square, which is the least opted for method. And then quadratic formula, which is usually somewhere in the middle. It's like, well, I don't want to complete the square, so I'll just do the quadratic formula, even though I don't like that one either. All right. So we'll try to factor, and if that doesn't work, then we'll try something else. So 1 and a 1, because that's got to be the way of it. 2 sine theta, 1 sine theta, or just sine of theta. Well, if this is going to play out the right way, I need to have a negative sign in the middle. So we'd be looking at outer product of sine theta, inner product of negative 2 sine theta. So that'll give me my negative sine theta. And then if we multiply these two bad boys together, we get negative 2 sine squared theta. All right. So then we can solve those by setting each of those equal to 0. So 1 minus 2 sine theta equals 0. 1 plus sine theta equals 0. So for the first equation, subtract and divide. Subtract the 1, divide by negative 2. We're looking at sine theta equals a 1/2. And for the second equation, sine theta is equal to negative 1. And so from those, we can get our theta values, leading us to, hopefully, in a very convenient and easy sort of way, our vertical tangents. So we just got to think, where on the unit circle would we expect a y value to be equal to 1/2? For what radian measures?
5/6.
Pi over 6. And what's the other one?
5 pi over 6.
5 pi over 6. All right. And so the negative 1, we've already established that that's going to be at 3 pi over 2. And we've also established that that's the location of the cusp, so I don't have to address that. So it's these two jammies here that are going to be our vertical tangents, the locations in terms of theta of our vertical tangents. All right. So I guess I'll just leave it there for a second. If you're not sure, you know, you've got these values, you're like, are they vertical tangents? Again, do the value thing. All right, so I go in this mode, it clears out my clear button. So pi divided by 6, enter. 1.3 and then 0.75-ish, all right? On your calculators, it actually plots the point on the curve also, so it becomes even more obvious. But if you just ballpark it, 1.3 is about like right here, and then 0.75, shoot on up, it's about right here. That seems about right. Right? And if you do the same thing for a 5 pi over 6, it's a pretty solid bet that that's going to put you over here, but, you know, verify. At least for your own satisfaction. Five pi, oh, that's not 5 pi over 6. 5 pi over 6. Negative 1.3-ish and 0.75, so that's right about here. And then up 3/4 of the way, so right about here. So we're looking at pretty solid evidence that our vertical tangents are at those locations. All right. Now, the directions. You're always going to want to be mindful of directions. I don't think you need me to tell you that. But it says find the points where r equals blah, 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 you know, horizontal, vertical, tangent, all that stuff. But find the points. So my way of thinking may be slightly inconsistent with other folks. I don't look at points as the same, you know, I don't look at it as a synonym for coordinates, all right? Other people do. I don't care about other people, all right? That's a general rule of thumb. Just very simple. No, that's not, I'm not that bad. But when I say points, I'm really just looking for an indication of where those important characteristics are, all right? So by stating 7 pi over 6, 11 pi over 6, you've given me enough. By telling me the angle, I know that you know what you're doing, all right? If I ask you for coordinates, I would have to then specify what kind of coordinates I'm looking for, all right? So I would be, on a test, I'm very precise about what I'm looking for. I would say, find the rectangular coordinates where blah has a horizontal, vertical tangent, or find the polar coordinates, all right? That's a little bit of a different story. Then you have to go the distance on that. However, the value function on your calculator will tell you the rectangular coordinates, all right? The table of values on your calculator will tell you the polar coordinates. So you're not really doing much more work by me asking the coordinates one way or the other, right? And honestly, I kind of settled on that philosophy because in the past, I've asked people to state the coordinates and then I forget to take off when they don't. So it's kind of a moot point on my end. So I'm just going to make it very clear that these are the locations of my final answers. And then that's really the end of it. And besides, if I wanted rectangular coordinates, I mean, this is a little bit of a different story because this function doesn't, this polar equation doesn't really lend itself very much to rectangular function form. But in most cases, if I wanted an answer in rectangular form, like, why would we have it in polar form to begin with? You know, like, that's just my way of thinking. But for the most part, the pre-calc world, building up to the point where we develop some fluency, and once we have that, when we hit unit 2 and unit 3, all of this stuff is going to work its way into every kind of problem. So, you know, imagine in unit 3 where we're looking at a situation where we have to work with parametrics and polar functions while also thinking in terms of vectors, right? So, in three-dimensional space. So we're building towards something here. It just seems very disconnected at this point, all right? But just like everything else, I'm not assuming that you have any experience with this, all right? So could be pretty boring for some of you. If you have experience in a physics class, then you already probably know something about vectors, probably more than we're even going to cover in this course. But I'm not going to make any assumptions. So a vector is a quantity that has both magnitude and direction. So if you're talking about speed, that would be known as a scalar. All right, so speed is a scalar. This is a classic example, even from physics. That's usually where they start. Speed is a scalar. Velocity is a vector. All right, because speed is really just talking about the magnitude of the velocity. All right, velocity is incorporating direction too. All right, but what happens is people use the term velocity in real life as just a fancier substitution for the word speed. You know, it's like, increase your velocity to 96 miles per hour. You know, it's like, okay, you're not using it technically correctly, but we get what you're trying to say. All right. If I'm saying the velocity is 96, I'm talking about a positive 96. I'm talking about 96 miles per hour in the forward direction, all right, or upward direction, depending on the nature of the space, all right. Whereas speed, if I say my speed is 96 miles per hour, it could be in any direction, all right. So it's just the magnitude of that. But we start with something pretty basic. Sketching a vector from point p11 to the terminal point 45. So here's 1, coordinate, point P, 2, 3, 4, 5. I don't need 5 there. 4, 2, 3, 4, 5. And what was the other one? Q? It's usually Q. Yeah. P's and Q's. It's always P's and Q's. All right. So this is a line segment. A vector needs to start at the origin. All right. The tail of a vector is always at the origin. So what I need to do, and it's a very visual approach, and you'll find that moving forward, a lot of the stuff that we're going to cover in this class is more of the visual variety. Like if you could get a sense of the visual characteristics, then things start working themselves out pretty nicely. Right? What I want to do is I want to pin this line segment at the origin using a translation. So I want to pin segment PQ to the origin using translations. All right, fancy word for shifting the points. All right, so if I'm going to shift point P, I'm going to go down 1 unit, and I'm going to go left 1 unit. So what I do to P, I have to do to Q. So down 1, left 1. So my Q prime is going to be here. P prime is going to be now at the origin. All right, the line segment connecting PQ is the vector PQ. All right, no matter where it is in space, that new line segment is the vector. All right, always having its tail pinned at the origin. All right, so Q originally was at 0.45. But what we did was we did a translation left 1, down 1 of point Q. And that gives me Q prime of 3, 4. So vector PQ, which we denote with a little arrow over it, kind of half an arrow, is represented just by the endpoint of that vector, which would be 3, 4. All right, that's a lot of like fancy notation. A lot of fancy notation, but really it's just saying, move the points over, find the endpoint of the new line segment, that's your vector, all right? Taking on the values of the original coordinates, PQ, all right? Now, you may be familiar with another form of the notation, alternate notation. You might see hard brackets 3/4, or you might see even curved brackets 3/4. They mean the same thing. I don't plan on using that notation in this class, but you walk into a linear algebra course. I don't know how many of you have experience with that, but if you walk, next semester, let's say you take linear algebra, you're going to learn about vectors again, fun fact. But they're going to use that notation because that's matrix friendly. All right, these create column vectors which go right into a matrix. All right, so you know you can get the properties and characteristics down from this course, but you'll have to get used to new notation.
Oh, so it's an X, Y, Z, X, Y, Z, it's X, Y, Z.
Exactly. Seemingly to make things as confusing as possible. Really, it just fits with the operations involving matrices that you're going to learn about in linear algebra. All right, so this really just kind of details what I was talking about above. You know, a lot of hand waving, but this formally addresses it. And this gives you a formula that allows you to figure out the component form of the vectors. All right, so how did I figure out the vector PQ up there? I found the difference between the two x values and the difference between the two y values, except I did it in a more geometric way. All right, so this is a little shortcut approach for doing stuff like that. So if you want to apply this in this situation, express vector v with initial point, this would be x sub I and y sub I. And this would be the terminal point x sub t and y sub t. Then vector v is going to be equal to the differences. So 1 minus negative 2, and then 2 minus also negative 2. So 3, 4. All right. If somebody's looking for typo opportunities, here's one for you. I have no idea why I have so much space after the definition. Vectors are said to be equivalent vectors if they have the same magnitude and direction. That is a fact. There is no need for any of that space below it. So I gave you space for that, but on that last problem where you could have used a little bit of more space, I did not. So I don't know what's wrong with me sometimes. But yeah, if somebody wants to submit that, just again, just on remind, just send me a message, page 18, under definition, remove the space. And I'll know what that means. Vector operations, adding and subtracting, very easy. You're just adding corresponding parts. Scalar multiplication, very easy also. You're just distributing the scalar multiple through the vector. All right, it's when you get into vector multiplication that things start getting a little crazy because there's a couple of different types. All right, there's something called the dot product and there's something called cross product. Definitely different subjects for a different day, but it's coming. And it's pretty procedural, but it can be a little mind-bending, somewhat mind-bending. All right, so I have vector m is equal to 5, negative 7, and n is 0, 4, and p is negative 1, 3. We want to complete the following operations. How does it feel? Compute the following. Forget the operations. That is just that the language is weird. Honestly, I think I copy-pasted that one from OpenStax. I don't like that. It's just awkward. Compute, hello.
Yeah, that definitely sounds like something in the textbook would have said. I think that's what it said.
Yeah.
First.
At the end of this course, you're gonna be like, I learned a little bit of Calc 3, but I really, really helped Professor Can fix his note packet. That's really why we're all here in the end. All right, so m, 5, negative 7, plus negative 1, 3. So very simple. Add the corresponding parts. No need to memorize a rule. I try not to overuse the term common sense, but this might fall into that category. All right? Like if I didn't give you any instruction and I just gave you these values and I told you to add m and p, this is probably what you're coming up with. All right? So intuitively, you already knew how to do this. Maybe even number 2. Except I wouldn't even show the step of actually writing 2 as a coefficient of m. I would jump right to doubling m. All right, so I got my m over here, 5, negative 7. I'm going to double that, so 10, negative 14. Then I got my n over here. I'm going to triple that, so plus 0, 12. And then the last one, I'm still going to use addition. I'm going to negate it just to make the addition ever so slightly easier. So 1, negative 3. I don't have to worry about mixing up operations. So 11. Negative 14 plus 12 is negative 2. Negative 2 plus negative 3 is negative 5. Oh, because we're subtracting. So it's a constant multiple of negative 1. So I negated this.
Oh.
Yeah, I just
I
measured
missed
that.
the.
Shit.
Negative 14 plus 12 is 2. What's
Negative.
minus 3?
Negative 14 plus 12 is negative 2. Right. There is a way to do this on the calculator. It's just more trouble than it's worth. So I think at this point, because you know how much I like the calculator, that when I tell you that something is not going to be good for you to do on the calculator, hopefully at this point you believe me, and we could just kind of skip that part of it. But GeoGebra is really great for this stuff. All right, so that's where things get exciting. So the graphical way of finding the sum of two vectors. This is something that I like to put on the test. It's another kind of, well, middle of the road kind of gimme question. It's not the 30-second one, but it's kind of like a step above that. Very doable, but people often fall into the trap of just not doing it the way that you're asked to do it. It says graphically find u plus v. All right, well, I can do it using arithmetic.
Oh, are you supposed to connect the two?
Yeah.
That.
I mean, looking at this, I say 6-4 and call it a day, but it says graphically do it. All right, so there's two ways to handle it. I like using the parallelogram approach. That's just my personal preference. There's a tail to tip approach that also works, but I don't like that one, so I'm not going to go over it that way. All right, that's just the way it is for me. So what you're going to do is, I think an index card or the side of a sheet of paper really gets the job done. All you're going to do is take the side of a sheet of paper. Oh, geez, this is perfect. Oh, wow, I couldn't have planned that either. I did not plan this. All right, it's exactly 11 inches long. All right, so what you're going to do, if the line segment were longer than the side of your sheet of paper, you just mark the beginning and end, and then just translate the whole segment over, and then plot a point, and draw a line segment. All right. So it's not going to help me to draw it here. I just need to kind of get a landmark below the O's and kind of in line with the top. Okay, I'll figure it out. So you're really kind of eyeballing it because I'm not looking for any kind of great accuracy, because you've seen my drawings. They're not good. And I'm generally, there are exceptions, but I'm generally a practice what you preach kind of person. So, like, I can barely function in the art world, so I'm not going to ask you to make anything too stunningly gorgeous. All right. So, plot a point that you think would represent what that end of the line segment would look like, and then use your line draw tool to draw a line segment, and then you'll be in pretty good shape, aka a ruler or something along those lines. Side of a finger works pretty well in the absence of a ruler. Side of a pen, I've done that. The index card that you use to mark things off, you could do that too. The slope looks a little off, so I'm going to redo it, but that's just a me thing. Yeah, maybe like over here, I think. Yeah, it looks a little nicer. All right. Then what you would do is the same thing with vector v. Translate that up and connect it. But once you've already translated one of them, you just connect the dots, and you'll already have the translation of the other one. All right. So that's this bad boy. That's not that bad boy. I think freehand is really. Ooh, that's disgusting. All right, so then once you have your parallelogram, draw a line segment going from the origin to the outermost point. That represents vector u plus v. So we label that up. that point should correspond with the actual sum of the two vectors.
Wasn't this just twice as much work as the tail though?
Wasn't it twice as much work as the tail to tip?
Yeah.
Maybe, yeah.
Isn't the tip and tail like just dragging the bottom one up to the top?
Or the top, or the
Right.
Yeah.
But what's going to happen, and so we got to do this in 3D. So this ends up being a little bit nicer in that regard. So, yeah, once you get that Z component in there, things start getting a little crazy. So, I've done it both ways, and I just kind of settled on this way as the way I like more. But I mean, if you know the other way, you want to do it that way, that's perfectly fine in 2D. I would ask you to keep an open mind once we go to 3D. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it's not even anywhere near. Oh, actually, no, that's perfect because I didn't include the numbers on this, but these are half units, right?
Yeah.
Yeah, because this would be 4-1, but it's 8 tick marks. So that actually works. And then 1, 2, 3, 4. Well, that's a little more. Oh no, these go by ones. So that's actually it's actually correct. All right. So let me label up the horizontal axis. I'm always surprised when my graphs end up working out nicely because it's just not a thing that typically happens. All right, and so we get u plus v is equal to 6, 4. All right, and again, you knew that from just doing the sum, but this helps you develop a visual. Now, I gotta tell you that people have done this in the past and it really, I mean, it aggravates me, but like not to the point where I'll lose any sleep over it because I just take off full credit and then I get over it very quickly. What people will do is, oh, you want graphically, huh? 2 plus 4 is 6. 3 plus 1 is 4. They plot 6, 4, and they draw a line segment to it, and they say, well, there's your graph. That's not this, all right? Yeah, I mean, that's, I guess, what people do when they panic, and they're like, oh, I meant to study this, but I didn't, and now it's here on the test, and he's gonna know that I didn't study it. I got an idea. This is gonna be on the test. Study it. I am going to put this on the test. Maybe even this exact question. I don't know. Something very similar to it. All right. One semester I put a 3D graph on there, and I would have had everybody's tests graded within a 24-hour period like I like to do. But because of that one freaking question, it took me like almost a week. Because 3D graphs, like even a crappy graph could be correct. And it's just hard to evaluate what's right and what isn't. So, yeah, on a piece of paper, yeah, it's a nightmare for me. So just for my own sanity, I'm like, you know what, I'm gonna put this concept on there, and I don't want to be spending the rest of my life grading it, so you're getting a 2D graph. You're not getting it. So maybe it's not 2 and 3, 2, 3, and 4, 1. Negate, I don't know, something like that, but maybe a little twist on it, maybe a scalar multiple involved, but it's going to be something very much along these lines. And so that, I mean, you can't get any better than that as long as you actually do your part and study it. This last one here, I'm going to put a star on it, but I'll just give you kind of a quick sense. It's asking you to use these actual line segment lengths. You don't have to use them in the position that they're in, but what you do have to do is take note of the length of vector v and the length of vector w and come up with these different relationships. 3w should be pretty easy, just triple this length. All right, and you can do it anywhere, probably separate paper, I would think. V plus w, you're going to use a similar idea to this. Just when you plot v and w with the appropriate lengths, just pin them at the same endpoint. All right, it doesn't necessarily have to be at the origin, it could be in space, but pin them at the same endpoint. And then create your parallelogram and go from there. This one is a little twisty, but I want to see if you can figure it out first before I give it away. All right, So that's where we're going to leave it tonight. And next class we'll do a little bit more with the derivatives of polars. I'll try to budget more time to do another area question with you, and then we'll continue on with this stuff. It's really just index card kind of thing. So for A, get my pen going. I'm just taking a length consistent with W and tripling it, all right? But remember, vectors have magnitude and direction, so I have to be consistent in the direction also. I can't manipulate that angle, all right? And later on in the course, we'll talk about how we can make use of the angles determined by vectors and stuff like that. It's pretty cool stuff. I do want to try something though, because I really feel like I should be able to trace over this and then just move that line segment, but I've yet to figure out how. Okay, I just figured it out. That's literally, I've tried it so many times, and that's the only time it's ever worked.
Keeps its orientation.
It does keep its orientation, which is really kind of cool for me. It doesn't help you all on a test, I guess, but you know, for you, it's just create on your index card a couple of tick marks and then just slide it on down. Or reality is, for a question like this, you might just add it right on and do it that way. You know, you can make use of the figure that's already produced. All right. So, yeah, this is what I wanted to see if I could do. I wanted to try to copy this and paste it and then move the new one. Let's see. No. I figure it's like a long press kind of thing. No.
What is the one with the little plus and the two cards above the figure? No.
You'd think if it was going to be anywhere, it'd be there, right?
But maybe like the plus one.
Yeah, that felt right. I thought we were on this. I thought you had it there. Okay, well, at least I know the other thing works, so I'll just do it. And then drag. Well, at least there's that. I mean, pinpoint accuracy. It's something. And then one more. Ooh, that one's a little out of whack. Just fit. All right. So each one of these is a W, but collectively 3W. All right. So that's not bad. The W, the V plus W. So for B, we do the same thing. Take a V. That is not my line draw tool. Take a V. Drag that puppy over here, wherever I want. Take my W. I'm gonna go red for those keep the score at home. And then we just do those the whole parallel line maneuver. Oh, I keep doing that. But that's pretty much how a line would be if I didn't have the ability to use an app here. And then, so we're creating the parallelogram out of it with, you know, reasonable expectation for leeway. You know, it's a little iffy, but nothing a few arrows won't fix. Arrows kind of cover up our inadequacies sometimes. As it turned out, yeah.
So we were supposed to build on already what the V to W up there was, or?
Well,
You-
this is me completing it.
Okay.
It's just because if I built on it repeatedly, I'd run out of V's and W's
Okay.
pre-printed stuff. And then what I needed to do, because I'm looking for V plus W, I have to find the resultant vector, so the diagonal coming off. So this bad boy is going to be my V plus W. Now, as it turned out, it was very rectangular, but that's because it looks like V and W are very close to being perpendicular to one another. So they would create a parallelogram that's very close to being perpendicular. And in fact, I mean, it's hard to tell, but it could actually be, when you put it together, precisely a 90-degree angle. But it's not like we're going to throw a protractor on it to verify, because it's not within the scope of the question. All right. The next one is 2V minus W. All right. So I'm just going to throw in a little intermediate step here. 2V minus W is the same as saying 2V plus negative W. All right, the reason I look at it that way is because I know how to do vector addition. Vector subtraction is really just adding two vectors where one of the vectors is just going in the opposite direction as it was initially. All right, so my start is going to be pretty much the same. I need two V's. I'll just pop it down here. I'm going to need another one. Get on there. Come on. There it is. I had a battle with that. I haven't had such a battle since summer of 2018.
Why is that?
Striped bass fishing. Yeah, those babies are hard to pull in. Sand sharks too, a lot of them. More sand sharks than I care to admit. But the striped bass, I mean, I'll show the picture one day. Like, you know, when you're holding up a fish that you caught, and like for the picture,
They move a lot.
yeah, they do move a lot, but then when they're so big that you have to shove your hand down its mouth and hold it by the gills, like through the gills, that, well, it hurts, but it's also giving you an indication of just how big it is and how heavy it is that you need to get that kind of leverage on it to be able to hold it.
It seems they're not that sharp, right? So there's only really.
Yeah, well, at that point, they were just like, they knew it was over. There was no fight left in them. Like, I wore them down just in the process of getting them on.
Are these striped bass freshwater or seawater?
Seawater, yeah. So didn't. Yeah, because it flows inward. But we did it in the sound. So no, this is pre-great white shark. You know, so I was thrilled about that. I was very scared. That's like one of my big fears.
What?
Great white sharks.
No, there's no sharks.
Sharks in general, but great white sharks in particular, because yeah, but that's what they make movies out of, you know. So that's what you see, like, oh wow, you know, a tiger shark will kill you too. I'm like, yeah, but they don't make a movie out of that. They make it out of great white sharks, and so that's where we're at.
Now they make sharks that don't even exist.
Yeah, what is it? The Meg? Yeah, Sharknado.
Didn't exist like.
Well, they don't exist anymore.
I know.
Yeah.
They did at one point though.
Right. But I was reading an article recently. They were talking about the inequity between male and female actors and like how much they make. And I think it was Daisy Ridley. And who's the 90210 actor? Ian something or other. The blonde hair guy. He's in Sharknado. But anyway, the storyline was that he made more for Sharknado than Daisy Ridley made for The Last Jedi. And I was like,
Sharknado's probably a better movie.
valid point. But it also implies that he made more for that than Force Awakens. Force Awakens I thought was pretty solid.
Didn't the actor who plays Tony Stark's like wife and Avengers get paid like she's like the second highest paid actor on the.
Yeah, it's just the name power. The
Yeah.
name recognition.
How much
Gwyneth
screen time
Paltrow.
did she get? Like 20, like a
Yeah,
minute or two?
And there was some where she just was named in the movie, and she didn't
Yeah.
show, Gwyneth Paltrow, Pepper Potts. Yeah. Well, Gwyneth Paltrow. She is famous enough without that role. Oh, Last Jedi.
But all of
If they could wipe that one from existence, psh,
all the actors from the Avengers movies get a lot of money.
when you make 23 of them,
Yeah, right.
yeah, like, and some of them actually ran the gamut, made it through like 10 movies or so. It's like crazy. So we got our 2V, and this is right here. This is my W, but I need a negative W. So I need that W, but going in the opposite direction. So I'm going to pop that in there. And I could have plotted that immediately, but I wanted to take a moment and really just kind of emphasize it. So
If you were to, like, an example like that in the test, do we have to show the W or?
you don't. You could jump right to the negative W.
Okay,
But for instructional purposes, I figured I'd show it at least this one time.
okay.
Yeah.
Would you be wrong by putting the negative W at the other end of the 2V?
No, you can put it. It's going to go there eventually anyway. So
With the result anyway?
yeah. So I'll put my negative W on the other side, creating that parallelogram, and then I'll do the same thing with 2V. I'll just kind of do it here and then move it over. Hopefully it'll work. And it did. So I got my parallelogram. And then again, we're looking for the resultant. So here to here, line segment. Hopefully it'll go straight. It does, good. Take a win. And so this purple vector is going to be my 2V minus W. All right. So it's like a little art class for you. Just, poorly taught, because, can you imagine? Like me drawing this by hand? I mean, like when I draw the line and forget to put the tool on and it comes out looking like this, that really is like how my lines come out. And that's just because I've lost like sensation. So this is like adaptive technology for me. Right? This is like a necessity. So yeah, straight edges I recommend. If you have, like if you're anywhere skewed in my direction when it comes to artistic ability, yeah, a straight edge is pretty helpful. Like I said, a side of an index card gets the job done, but yeah, something.
I'm a bit confused with the way you drew it. I mean, for the diagonal, why didn't you go from negative W to the?
So this is the point where all the vectors are pinned.
Yeah.
Your resultant vector is always going to go from that location. Same idea here. Oh well, it was irrelevant there. All right. So once you create the parallelogram, you know where it's pinned. It's always going to go to the opposite vertex. So once you have your two vectors, you create the opposite sides, you know where it's pinned, find the vertex that's on the opposite side of that, and then that's your line
Yeah,
segment.
I get it if you do this, I just do it from the triangle side, because I know exactly you gotta move. But doing it with the parallelogram, it's a little bit confusing. Can't seem to figure out
Right, so-
exactly what's the steps that's leading to.
Let's say I didn't draw these two line segments, then you would have your triangle here,
Right.
and then this would be your resultant vector. All I'm asking you to do is throw the opposite sides in there too. So if you want, draw it the way you like it with the triangle approach, and then just throw two opposite sides on it and make it a parallelogram.
Is this fun?
I really have to think about it because it looks a little bland, but it could be perfectly fine. Yeah. Because mine's all colorful and everything, so I'm like,
Like,
I'm
I know
comparing
I-
my jazzed up version to that, and I'm looking
I know
at,
we don't have like a result.
yeah, the resultant is like an absolute necessity.
Yeah, well, I thought when it said sketch of vectors, I thought it just meant sketch.
Oh, well,
W.
V plus W, the sum of two vectors is the resultant vector. So that part needs to be there. So when you have these two legs, that's fine, but you gotta have that resultant in there too. Right, so that's the part, that's the spice that's missing from your diagram. Then it'll be more flavorful and we'll be good to go. Right. It's the chocolate chips in the cookie. Yeah. I got all these kind of food analogies. I can do this all day. So, magnitude of algebraic vectors. Magnitude is based on Pythagorean theorem. So, that's really all there is to it. If you're dealing with, I'll just draw out a quick example. I'll keep it simple. Let's say you have vector 1, 2. And I want to find its magnitude. The magnitude is just talking about the length of the vector. All right? So the way we denote magnitude is just by putting a double absolute around the vector itself. All right? If the vector is written out the way I have it here, as in numerical form, that's how you write it. But if we denote the vector as a variable, like u equals vector 1, 2, then you can put the double brackets around the u. Right? So the double bracket just means the magnitude of that vector. Right? Some people use a single bracket. I don't particularly care for that, only because sometimes we're going to find the absolute values and also the magnitudes. So absolute value is a single bracket, line brackets, and the magnitude is double. So you're going to take an absolute value and then do this. It's going to be confusing. So if you were using the same notation for each one. So double lines represent magnitude. That's the long and short of it. All right? So I'm just going to draw a very quick sketch. Plotting 1, 2. Line segment. So this is my vector 1, 2. The magnitude of this vector is determined based on the length of that line segment. One way that you can get that length would be to decompose the vector into its components. All right, we have a horizontal component, which has a length of 1, a vertical component that has a length of 2, and then the hypotenuse, which we could call R. You could call it anything you want, but typically it's called R. All right. That might sound like it's designed to confuse you because we just got through using R for something completely different in polar form. It's just any distance from the origin in space could be thought of as a radius. And any of those distances could be thought of on a polar scale. And so this is just allowing for the flexibility to convert back and forth when dealing with vectors from rectangular to polar coordinates. All right, so it's kind of a tease for what's to come. Eventually, we're learning about rectangular vectors. Eventually, we're going to learn about vectors as they apply to polar coordinates, parametrics, and things like that. All right, so R squared would be equal to 1 squared plus 2 squared. So R would be equal to the square root of 1 squared plus 2 squared. So the square root of 5. That's the magnitude specifically of 1, 2. Come on, get in there. Oh, you know what? It's when I get to that corner. That's what. Nope, my pen just turned off. All right, so that's our magnitude because that's the length of the hypotenuse. So magnitude and direction make up the characteristics of a vector. Now we haven't really talked about direction other than to say, it's 1, 2. So it's going 1 this way and 2 that way. But we're eventually going to get to a point where we're talking about an angular movement because I could figure out what this theta is in here. I can just use a little SOHCAHTOA action, right? But that's a different story for a different day because I want to do that as a lead-in to the three-dimensional analysis associated with the magnitudes and things like that. Maybe a different day, maybe a different like minute. I'm not sure. I can't remember when I do it, but we do it, just not now. All right. So this example is just asking you to find the magnitude of vector v and then apply some properties. Those properties are just asking you to take the magnitude. So here we're taking the magnitude of v and then multiplying it by 5. All right? But the other one is telling you to first multiply the vector by 5 and then find its magnitude. So it's really asking you to find the magnitude of negative 30, comma, negative 40. Now this is not a proof, but it's definitely a justification, all right? So for A, when they say find the magnitude of vector v, it's the square root of the squared values added together. Now if you were to draw this out, you'd get a nice 6, 8, 10 right triangle. So you don't have to show the work if you happen to know that Pythagorean triple 6, 8, 10. But that being said, negative 6 squared is 36. Negative 8 squared is 64. Add them together, you get 100. And then take the principal square root. All right, because the magnitude is going to be an absolute measure. All right, we're not looking for positives versus negatives. The direction will give us, you know, by finding the theta value, by finding the coordinates, that'll tell us which way it's going. All right, and not only that, if I say v going in the direction of negative 6, 8, negative 6, negative 8, I'm defining that as the positive direction for this scenario. So the opposite direction of that would be the negative direction. All right? It's just like being in a car. Forward is forward. Doesn't mean that you have to be going north in order to be going forward. Forward is forward from your perspective. All right? You could be driving up a mountain. You're still going forward from your perspective. All right? That's how it works with vectors. Now for B, 5 times the magnitude of V is really just saying 5 times our answer to part A. So 50. Nice and easy. C is telling us when we're finding the magnitude of 5V, we're finding the sum of the squares under the root going to be the same thing, because you get 900 plus 1600 is 2500, the root of which is 50. All right, so what we just learned is that 5 times, so therefore 5 times, and they didn't ask for this, but I'm going to state it anyway, 5 times the magnitude of V is equal to the magnitude of 5V. All right. So this implies, now again, it's not a proof, but we just showed a case where it seems to work. Will it work all the time? That'll be the reason why we would do a proof. It implies that some scalar multiple C multiplied upon the magnitude of V would be equal to the magnitude of that scalar multiple upon V. All right, and in fact, I would even elaborate and say that this would be one of those triple equal signs. That means equal by definition. All right, which is a legal move when you're doing a proof, because what that's saying to the reader is that these two things are equal, not because I demonstrated it anywhere here. They're equal because it says so in a published textbook somewhere, and I studied that piece of information. All right. So if it's a rule, you could use this symbol as part of a proof. It's a little too fancy of a symbol to use for ordinary mathematics, but I would say as part of a proof, this is a legitimate approach, and I'll show you some situations in a little bit where that comes into play. I have not needed this for a while, so I apologize for that. Undo. A little stray Mac right here. And it just froze on me for a sec there. So speaking of properties, we have the commutative property. You can add in either order. You have the associative property, which is basically kind of talking about the same thing. You can group it any way you want, you're still going to get the same sum, but only for addition. You have the additive identity property, right? If you add the zero vector to some vector u in 2 space, 3 space, 10 space, doesn't matter, the result is still going to be the original vector u. The additive inverse, so add 2 opposite vectors, you get the zero vector as a result. All right. Another example of associative property, but this time for multiplication. And you have distributive property, variations of distributive property. One for vectors, distributing a vector upon 2 scalars, and then distributing a scalar upon 2 vectors. And then the last one is the multiplicative identity property. But I wanted to take a second and talk about the concept of the zero vector. Because you see the 0, and it very often looks like just the number 0. The little notation here, I'm going to highlight it. A vector whose entries are all 0 represents a 0 vector. So for this one, that is not a pen. I could do just a quick proof. All right, so proof in real space dimension, I'll use dimension 3. All right, so in 3 dimensions. So I have vector u. U would have 3 components to it. It would be u1, u2, and u3. All right. Now, I write it that way because the 1 represents the first dimension, or aka the x. The 2 represents the second dimension. Also known as y. And then 3 would be the z dimension, or the third dimension. All right. We use subscripts because if you start getting into actual letters, so third dimension, the z dimension. Like I could have said u equals x comma y comma z. The problem is, what if I want to go into 4 dimensions or 5 dimensions or 6 dimensions or 7 dimensions or 10 dimensions? I run out of alphabet pretty quickly. All right, so we use subscripts so that we don't have to bother with that sort of thing. So this proof is really just saying, because again, it's telling us that u plus 0 equals u. So I'm going to take u1, comma u2, comma u3, and add to it the 0 vector, but it's in real space 3. All right, so 3 space, which means that there will be 3 components to my 0 vector. All right, so just think of it this way. You're talking about the origin in the XY coordinate system. Coordinate 0, 0, right? We call that location 0. But its coordinates are 0, 0. In 3 dimensions, location 0 is coordinates 0, 0, 0. 4 dimensions, it would be 0, 0, 0, 0. All right, so why would the vectors be any different? All right, so now when I'm adding the corresponding parts, so that just looks terrible, so I'm not going to do that. So that looks even worse because that's not even a pen. So I'm going to add these 2. I get u1. I'm going to add these two, so I get U2. And I'm going to add these two, so I get U3. Throw some commas in there, put my little arrow brackets, and this would be equal to U. All right? And so I have proved that particular identity. And it's a rigorous proof, but I only proved it in R3. Now, I can get into the idea of a sequence. So I can do U sub 1, U sub 2, comma, U sub 3, comma, dot, 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 comma, U sub n, and then 0, comma, 0, comma, 0, dot, 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 end with a 0. And then add them up, and I can prove that this is true for real space n, which means any dimensional space. But, yeah, I think that might be a little overkill at this point, but it definitely is a fairly, I'll call it an easy proof, because, you know, like, I mean, I don't know too many people that consider proofs in and of themselves to be easy, but as proofs go, this one could have been a lot worse, so it's not bad. But basically, any of these problems, it really just amounts to you coming up with a set of coordinates to make up your vector that are consistent with the space that you're working in. All right? So, and it's fair game for any of these. Fair game meaning any of these could be on the test. So I'll ask you, you know, I'll give you a couple to try on your own so that you can familiarize yourself with them, and then we'll go over those next class, and then I'll give you a couple more to try, and you know, you get the idea. So I think you should try the commutative for addition, and I think you should try the distributive, this particular distributive, and I think you should try the multiplicative identity. All right, so try these. Because again, general theme that I like to follow is you try first so that you can experience it, and then before I give it all away. So try these. And honestly, you know, it's kind of like a full disclosure thing. This is really me just trying to trick you into studying the properties, because people just tend not to study them and they pay a price.
What's the D in 5? I don't understand that. Sorry.
Which one?
Number 5.
Number 5? Oh, C and D are both scalars. So they're not vectors, they're just some numerical value.
Oh, okay.
Yeah, so when you apply a proof and if you try to do it with 5, 6, or 7, the C's and D's are just going to stay as is. So you don't have to come up with a vector for that because they're just scalars.
C and D is just scalar.
Exactly. All right. So the example below is actually applying some of these properties. So I kind of feel like maybe it'd be premature to go over this. So I'll just put a star on that, and if you have time and you can tackle that, give it a shot, and we'll go over that one next class also. But here's that discussion of angles I was talking about before, where I said it's a different story for a different day, maybe a different minute. I was right, it was a different minute. All right. Component form of a vector using trigonometry. All right. So this right here, this first triangle is a unit circle triangle. All right. So this is a triangle that one might find in the unit circle somewhere. If it's a 30-degree angle, you would know what the dimensions are. You'd have a radical 3/2 and a 1/2. If it were 45, it would be radical 2/2, radical 2/2. But here, it's just a hypotenuse of 1. The reason why I know it's unit circle is because of that hypotenuse. Or at least I know that it can be applied to the unit circle is because of the hypotenuse. All right, that hypotenuse of 1 indicates a radius of 1, and a circle with a radius of 1 is by definition the unit circle. All right, so I have sides of this triangle that I can denote. I got an x and I have a y. All right, so I'm just going to go back to like early discussions related to the unit circle. All right, and one of those early discussions was that cosine of theta would be equal to adjacent over hypotenuse, x over 1, which would imply that x is equal to cosine of theta. All right. I would also have sine of theta is equal to y over 1, which would imply that y is equal to the sine of theta. Now, a vector in rectangular form is in the form of x comma y. All right? So this is what we call a unit vector. So I'm going to just tack that on, a unit vector, because this is one unit. All right, so if that one unit would be the hypotenuse of the unit circle, then that one unit would be associated with a vector known as the unit vector. All right, still with dimensions x and y, but x is specifically going to be cosine of theta, and y is going to be equal to the sine of theta. All right. And so what we can draw out of a conclusion as a conclusion for this is that any vector that falls on the unit circle would necessarily have to be a unit vector. All right. So vectors that, instead of saying fall, I'll say terminate. On the unit circle. But we could use these for other things too, but this is really the origin story behind the concept of the unit vector. That highlighter, it's like the worst thing ever. Like, what is the point of that? I mean, I could try the yellow again, but I feel like it's just, yeah, it's like it's not highlighting, it's just smearing it. But it's perfect over the text, but for some reason over like marker, it's just terrible. Like, look at that, good looking highlighting going on right there. But here, yeah, it's just like it's like I'm using magic marker right over it. It's like nothing.
Maybe you just put the highlight down on the outside.
Yeah, I don't even know. Yeah, it's blending the colors. It's just awful. Maybe.
What if you wrote over?
Like, then I'll have like. No, you see, it's not even blending there. It's just garbage.
What if you use the one below it? Like, you see how one has boxes behind?
Oh, like this?
Yeah. I don't know, try it.
Oh, but when I put it on highlighter, that goes away. Yeah, I think I'm just crap out of luck here. Oh, and now I left the highlighter on, and that's just going to aggravate me. All right, so now we have just a vector. It's not a unit vector. It's just any kind of vector. But the same relationship would hold true. We'd have cosine of theta is equal to the adjacent over hypotenuse. All right, now if I solve for x here, I get the magnitude of v multiplied by cosine of theta. Then if I do the same thing with sine of theta is equal to y over the magnitude of v. Again, SOHCAHTOA, it's all SOHCAHTOA. Y is equal to the magnitude of v times the sine of theta. And so this would not be a unit vector. This is just any vector. So the vector normally is in the form, I guess I can make that as an E, again, of x comma y. And we just established that x is the magnitude of v cosine of theta, and y is the magnitude of v sine of theta. Now we could clean that up a smidge because magnitudes are scalars. When I find the magnitude of a vector, it's a number, right? It's a fixed quantity, a scalar quantity. One of the properties, oh, I lost my double jammy here. Just put it in there. One of the properties listed above allows us to distribute scalars across vectors, or we can go the other way and factor them out. So I can pull out the magnitude of v and have a cosine theta comma sine of theta. All right, so this part is the unit vector. And together we're looking at the component form of a vector. All right, so it becomes a rule. I mean, everything becomes a rule at some point. And this is a derivation, but you can think of derivations and proofs as being very similar to one another, except the idea is the derivation is more of the origin story behind the formula. The proof is the justification that the formula works in all cases. All right. So, but they have the same look and feel in a lot of cases. You're working in general terms to draw a conclusion about something. All right. So these examples are pretty straightforward once you have those formulas, because this is find the component form of a vector with a magnitude of 4 that forms an angle of negative 45 degrees with the x-axis. All right. So negative 45 degrees with the x-axis. I'm just going to draw a quick sketch.
Wouldn't it be
4 divided by the square root of 2? It's going to be close to that, because you're going to have radical 2 over 2, so the 2 will go into the 4, so it's going to simplify a little bit. But let me draw the negative 45, which is going to go right now. Now, I'm looking at, so this, again, this is negative 45. But I want to be thinking in terms of positive coterminal angles. So the positive way to get to the same location. All right, that tends to make life a little bit easier if you're doing stuff by hand. If you're doing it on the calculator, it makes no difference whatsoever. All right, but most people, when they think in terms of unit circle stuff, they're comfortable with the 0 to 360. You throw in a negative angle, and sometimes it throws people for a loop. All right. So we have the magnitude of 4. So we're looking at 4 times cosine 315 comma sine of 315. So 4 times. And again, this is component form of vector. We're not looking for the magnitude of this vector. We already have that, actually. So we don't have to worry about Pythagorean theorem. That's already done. All right. So 45 degrees in the fourth quadrant, we're looking at coordinates of what? Radical.
You want it in radians?
The angle doesn't matter if it's in radians or degrees, because once you find the cosine or sine of it, it's going to be a ratio anyway. It's going to be like a radical 2 over 2 or radical 3 over 2 or whatever. So it's when you're going the other way, that's when it becomes important. So if I knew the ratio was, let's say, for example, 1/2, then I would want my answer in radian form. But if I'm given the angle, then it doesn't matter because I could just pull it off the unit circle. Right. Now, if you're typing it in the calculator, that becomes a big deal. Because if your calculator's in radian mode and you type in cosine 315, you're going to have a problem. Right? So you got to make sure that you convert the mode over. All right, it bought you enough time. What's the cosine of 315?
Negative root 2 over 2.
Negative root 2 over 2? Yeah, it's going to be a positive root. And then negative, yeah. Cosine's positive in the 4th quadrant. And then you can leave it like this. This is a component form. Or you can run through with the 4 and come up with 2 root 2 and negative 2 root 2. Either one would be acceptable. More than acceptable, completely correct. So if you look at this and you feel as though it seems familiar, like I feel like I've done this, it's because this is the same strategy that we used when we were converting back and forth between polar and rectangular coordinates. R cosine theta, R sine theta. That's what this is. Except this is my R. The magnitude of V, that's the R. All right, before when we were working, I forget where I drew it, but the hypotenuse of a triangle, maybe it's above on this page, I don't know. But the hypotenuse of a triangle, we typically denote that using the letter R. All right, here I'm calling the hypotenuse the magnitude of V, but it takes on the same role. So by finding the component form of a vector, you're really finding the polar form of that vector. All right. So if you know one, you know the other. It's just a matter of getting the notation down. All right. So this is pretty much the same kind of question, except they give you a positive angle, so that's even better. The one thing that you want to be careful about, in this case, it's not a problem because I'm not about to try to trick you on the first day of learning something. Just be careful, because it could say forms an angle of 120 degrees with the positive y-axis or the negative y-axis. You know, it could be a kind of a trick question there. So, and then when you get into contextual situations, it's like you start getting into like 20 degrees west of north and things like that. You know, so just be careful about the wording of the question. But in terms of the technique, there's no difference from one question to another. So I'll put a star on the next one.
A ladder forms a 35-degree angle with the wall.
What's that?
A ladder forms a 35.
Oh yeah, I mean it wouldn't be a math class unless we had a ladder against the wall. So that's gonna happen. We're gonna have a question where we have a piece of cardboard, cut out the corners, and fold the sides up to make a box. We're gonna do that too, because that's been in every class you've ever taken, right? So also, because like it's not a math class without that. All right, so this should be the last thing we do for tonight, because I'm getting tired. So we're all getting tired. Right? We're all tired before class started, but now we're really tired. So this is just really a formal discussion related to unit vectors, and that happens. I like to do that sometimes, where we talk about the concept and then I formally address it. It's a good way to go about it, because if you have it down intuitively, then this is just telling you stuff you already know. But if you didn't quite get it, then this is going to help you get it. Unit vector is a vector with magnitude 1. For any non-zero vector b, we can use scalar multiplication to find a unit vector u that has the same direction as v. To do this, we multiply the vector by the reciprocal of its magnitude. That's wordy. Here's the formula. That's really what it comes down to. But I really want to just kind of take a minute and get into what this is really telling us. All right? And so I'll start off with a simple example. And also, by the way, while we're here, we'll talk about the IJ notation a little bit. So if we call a vector vector I, this better say those packages came. I got a notification yesterday saying, sorry, we tried delivering your packages, but nobody was home. Delivered, okay.
We'll try again tomorrow at the same time, make sure nobody's home.
Yeah, exactly. But it was like 8:16 and I was standing by the door.
UPS.
Yeah. I'm like, you're lying. And it killed me because, and I knew I was standing by the door at that time because there was a commotion with the neighbors. Yeah, like that's the only break they're getting on this, that they drove up and they saw a bunch of cops hauling somebody out and they're like, yep, we're not going there today. And that's all I
Maybe he
do.
has any traffic violations, so they'll pull him over and say, okay, take him in.
Yeah.
Like
It's like
45
like an
license
Ant-Man where
plate.
they're driving down the street. Like, just back it up. Just back it up. You see all the cops are all like ex-cons. Like, just back it up. Just back it up. Let's get out of here. Like, that's probably what it was. All right, that's the benefit of the doubt I was looking for. Because the whole world can't be going straight to hell. I mean, it's possible, but... Like the guy this morning, I'm behind him at a traffic light, and because we live in the tri-state area, you're behind somebody at a traffic light, the light turns green, what happens? Yeah, I have to honk at them. Why? Because they're on their phone, right? So I give it like a light chirp. Like, I'm not a horn blarer under any circumstance. I just go beep, like a quick one. So this is what this guy does. He guns it, and so I start proceeding, and then he slams on the brakes. And I'm like, do you not understand what just happened? Like, I'm just trying to, like, I'm more confused. I'm like, wait, you think I did something wrong by honking at you? Like, that's how demented you are? And then I thought to myself, I'm like, yeah, it's the way of the world. He's going to do that to the wrong person, and they're going to follow him to work.
You're gonna do it to a tractor trailer.
Yeah, he's going to do it to the wrong person. I'm not the wrong person because I'm like, well, I had to deal with you for 1 minute. You have to live the rest of your life dealing with yourself. So I'm fine. I'm just going to go to work. But I'm just thinking, like, that might not be tomorrow, might not be next year, but somewhere, somehow, he's going to do that to the wrong person. He's going to pay a price.
What kind of car was it?
I think you know. It's always the same car. All right, on three. Everybody say it. 1, 2, 3. Audi. Wait, what the hell? Where were you on that? I was the only one. Ah. Well, none of you had the guts to say it, though. I'm the only one that went for it.
Is it really always Audi?
It's always an Audi. It's
No way.
every time an Audi.
It's better than
BMWs are like speed demons on the highway and everything like that, like ducking and weaving through traffic.
It's
But
better than the
the,
person
It's that
who was
angry-
at the light, the red light, and just kept rolling back. And
Oh, that's because you're stick.
like they
Yeah.
no, they weren't. It was an automatic. They just didn't have their foot all the way on the brake.
but how does
It
it
was
roll
on- it was on
back?
the hill
That's
for-
not how that works, though. It had to be a stick. Because
No, it,
Yeah.
was, it wasn't a Jeep.
then it's a piece of crap, too. Like the transmission is shot. Because
Engine brake is red.
Because their brake lights were on, but I don't.
it
think
rolls
they-
backwards?
No, it won't let you roll.
Yeah, that's what I thought, yeah. Like it'll go forward, and even if it's on an idle, it'll still go forward. It'll never.
It sticks, like I have a standard, and it gives you a second and a half. You take your foot off the brake, the brake stays on. So it gives you a chance, if in case you're on a hill,
Right.
light, the brake stays on for a second after you take the foot off the brake. Give you a chance to.
Yeah.
I have a theory why it's always Audi. So they wanted a sports car, but they couldn't afford a BMW, so they said Audi. And now they're just so angry for no reason.
They see all the BMWs out there and they're like, damn it, they got the wrong one. You know what? I saw an Audi open its car door, and apparently they have projectors in the door that project an Audi symbol on the
You can buy
ground.
those, you can install those.
I'm like, how pretentious is that? Like, honestly, sometimes there's parts of me that are like, you know what? If there's an Audi driver in here, I don't apologize. Like, you know what? you know who you are. You're the worst driver in the world. I mean, right up there with Kia drivers and like.
I find the Subaru WRX driver.
Oh, the ones that take the mufflers out on purpose?
They all think they're Travis Pastrana, like a rally course.
Yeah.
And they have the lawnmower sounding muffler.
Yes, yes. That's troublesome also. Yeah.
I'm not saying anything bad about the car. I'm saying the drivers.
Yeah.
All think they're hot rodders.
Honestly, it's the train of thought that enables a person to say, you know what? I know this has got a muffler, and I know what mufflers are for, to muffle sound, but I'm going to take that out. I'm going to put one in that not only is going to allow the natural noise of the car to happen, but I'm gonna put one in that magnifies and amplifies that noise. I want it even louder. Like that's, yeah. I don't know who you are.
I know it's
Is that you?
No.
Is that you?
I don't have that. I've been in like different, like, cause I have different friends, right? And some of them are pretty wealthy, right? So they have like nice cars, and I'm not gonna lie, when you have like a muffler that makes a lot of noise, and you're driving the car, because I've driven a BMW M4 that had like really big, like it was really loud.
Right.
And like when you're driving, you give it gas.
That's not the muffler.
You're not.
You feel cooler?
That's an exhaust. That's not.
Oh, you can
that's
exhaust. There we go.
Oh yeah.
It's not a bolt-on piece of garbage muffler. That's the exhaust that's tuned to sound good.
Yeah.
Like the engine. That's not.
Yeah.
It's the horns that sound like the truck that really bothers you at night.
Yeah.
You think you're getting off the exit, all of a sudden you hear this truck horn coming out you.
Oh.
And then you see a little Hyundai driving up right next to him. And you're like, what the hell just happened?
When you have a good exhaust and it sounds good, you not only hear it, but you kind of feel it. So like as you're accelerating, it also gets louder and faster. So like, you kind of feel the energy, like you feel the power.
Oh yeah, a little extra authority. Yeah, I got you.
2-hour ride. You got one of those mufflers.
I guess that's probably. I'm just gonna keep going with it. I think it's worth it. So anyway, so this vector here, this I vector is vector 1, 0. And then vector j is 0, 1. As indicated by the coordinates. So really we're just stating what the coordinates are. But just as a shorthand way of expressing it, we would say I and j rather than writing 1, 0, and 0, 1 over and over again. All right. But in terms of finding a unit vector related to a particular vector, this is like the beginning of the next phase of the unit, which allows us to really kind of get, really explore the concept of a vector. Let's say you had, for example, a vector 3, 4. All right. That vector is not a unit vector because you can tell immediately that if you were to square these two values and add them together, you're not going to get a 1 as a result when you take the square root. So, but I will find the magnitude. I'll call this, well, I can call it anything. I'll just call it V to keep it in line with the formula. All right. So V as a magnitude would be the square root of 3 squared plus 4 squared, which Pythagorean triple. 3, 4, 5 right triangle. All right. So U, the unit vector U, would be equal to that vector V multiplied by 1 over its magnitude. So 1 over 5 multiplied by vector V, 3, 4. Or we could run through with the 1/5 and call it 3/5, 4/5. All right. Now I'm just going to verify it. I can find the magnitude of U. That's going to be equal to the square root of 3/5 squared plus 4/5 squared. So 9/25 plus 16/25 is going to be 25/25, which is 1. Square root of 1 is 1. All right? So we just created a vector that's going to have a magnitude of 1. But then you ask, okay, wait a minute, why? What was the point behind doing that? So I'm just going to draw a quick sketch. Always a quick sketch. It's never going to be anything too elaborate. The only thing that I might ask you to do, it's like a point-by-point kind of thing, would be a polar graph. Everything else is going to be just a quick sketch. All right. So I could plot 3, 4. Let me just bring it in a little bit. 1, 2, 3. 1, 2, 3, 4. And draw a line segment corresponding with that vector. That's vector V, which looks like a check mark, so let me fix that. And let me make this look more like a check mark. All right. Then I could plot 3/5, 4/5. So 3/5 is 0.6, 4/5 is 0.8. So if I'm starting at the origin and I go over 0.6, so it's going to put me about right here-ish. 0.8 will put me about right here. If I line them up, that's going to put me on the line at this location. All right. So that little line segment, that little bit of line segment there, that's the unit vector u. All right. So the unit vector has the same direction as the given vector. All right, which means that that unit vector actually forms the basis for that original vector, telling us that we can write that original vector as a scalar multiple of that unit vector. All right, but we're not just limited to doing that. I could write any vector along this pathway as a multiple of this unit, because this becomes the increment of measurement for that vector system. All right, so if I needed to go out 10v, I can count in terms of v's, or I can count in terms of u's. The benefit of creating a unit vector here is I'm able to standardize. So if I needed to create a unit vector for some other vector, I had 3, 4 here, maybe I have 5, 12. I can create a unit vector for that. Now I can take two things that are apples and oranges and standardize it so that it's one piece of fruit, one piece of fruit. All right, you're looking at two things that can now be compared to one another. All right, because their increments are in terms of magnitudes of 1. So then I can actually make a determination of the relationship between those two vectors. Now, at this point, it's without context. So a lot of that is just hand waving. It's me saying, yeah, we can compare them all on a same scale. Wonderful. What is this going to be used for? We'll talk about that next class. All right, so that's where we're going to leave it tonight. And we'll continue on. I'm not going to star any problems on this because I've barely scratched the surface on that. We'll wrap up the unit over the next class, and then we'll start talking about review for the test. All right?
Test is first week of October, right?
Yeah, which is next week.
Next week?
Yeah.
Next week of...
So Wednesday next week. So a week from tonight. All right, so I got everybody for attendance, so if you have any questions, stick around. Otherwise, see you on Monday. And we'll try not to get run off the road by another Audi driver.
On Monday, are you going to review like primarily like what you want proofs of and stuff like that? Or?
Yeah, I'll give you the breakdown of what I'm looking for in terms of the proofs. Yeah,
Thank you.
no problem.